Keeping series of the seminar, and let's begin.
Thank you. I'm very happy to be here. I will give several talks on this subject on how to extend case theory and other localizing invariants to certain large categories, and give a lot of examples of this. But I will start with the kind of usual picture. So the usual picture is, let's say, in algebraic geometry, we have let's say quasi-compact, quasi-separated scheme, and like we can associate category either we can associate with it the large category, drive category of quasi-coherent sheaves, well, OX models with quasi-coherent homology, or can associate the small category first complexes. Yeah, and okay, if the scheme is not theorem, we can also consider a variant like derived category of coherent sheaves. But in general, so these are two basic options, and in fact, they contain the same information about the scheme. So basically, more precisely, the perfect complexes can be reconstructed and just by taking the compact objects in the large category. And the large category is the incompletion. So basically, it doesn't really matter which category you associate. So I mean, it just depends on a particular problem which you're interested in. So they contain the same information. So when people talk about usual invariants of schemes like case theory, like quotient homology over some base, or quotient homology over the absolute base, and invariants. So basically, what happens is we apply like the corresponding invariants to the category of perfect complexes. So this is like the modern way to think about this invariance applied to algebraic geometric objects. Okay, more generally, this don't move. More generally, you can take any like DG algebra or E1 ring. So yeah, you have this category of modules over. You have perfect modules, and again, so this is like whole category is incompletion. Category of perfect modules, and again, like case theory ring, like that to be the same as case theory of the category of perfect complexes. So this is like the usual picture, but what I'm going to explain is that there's a number of situations in which like you cannot really associate any reasonable small category. So I mean, in particular, they use this invariants like algebraic case theory and other standard invariants. They don't really make sense, the class of examples which I have in mind are coming from, for example, rigid analytic spaces, coming from topology, and also from complex analysis as well. So in this kind of so there's a large class of situations in which kind of the usual categorical approach doesn't really work. Like, for example, like coherent sheaves on a complex analytic space, I mean, they don't make much sense from this point of view. And so, okay, so roughly speaking, so the goal.
I'm sorry, I have a question related to my point.
Yes, sir.
So what is the notation for the subcategory of compact?
Well, it's omega, where
Ah.
omega is the same as aleph 0. Yeah, but people, yeah, this is the same as just C. Like I think the more classical
Okay, it's omega.
yeah, omega, yeah. Yeah, so compact objects, yeah. So goal will be basically to extend the scope of localizing invariants, such as K-theory, to a certain class of large categories. So more precisely, we will define for sufficiently nice large categories. So we will define what I call continuous K-theory and other localized invariants, and in such a way that if C is completely generated, so if C equals to the incompletion of the subcategory of compact objects, then
No, I understand. I understand. But I hope it goes well. Yeah, it's a risky thing, but I hope that the other co-founder is
Mute. Apologies. That was a
okay. I thought it was a question.
no. Sometimes people do unmute themselves for a question, but
Okay. So the point will be that if C is completely generated, then this new continuous K-theory is just the usual K-theory on of the subcategory of compact objects. So in particular, so for example, it's just continuous K-theory of modules, the whole category of modules. I mean, DG modules or applicable spectra and module various spectra. This is just the usual K-theory of the ring. Yeah, I will define what I mean by this certain class. So I will explain which categories I will consider. But actually, before that, I will maybe give examples of.
And
of
an
this.
important message is that this class, which we call subclass,
Yes.
is important.
Yes.
It's actually we knew it before because Louis explained.
Yeah, I mean, this class itself is not new.
There were other people.
Yeah.
But the message is that this class is even more important than it follows from this.
Yeah. So this will be, in fact, what is known as dualizable, dualizable presentable, or also equivalently compactly assembled categories. But before recalling what they are, I will give some examples of this. So one class of examples which we will consider is so if so X is a locally compact Hausdorff space.
Wait, can we agree that all locally compact spaces are assumed Hausdorff?
Yeah, we can do that. Yeah, I mean, actually, there are examples of this when the space is not Hausdorff, but we can just reduce to the let's just assume that everything is Hausdorff unless otherwise stated here. So locally compact Hausdorff space, and we can take the category of sheaves of complexes of abelian groups. As an example, okay, let me just make a remark. I will maybe recall this later, but this is not the same as, in general, it's not the same as derived category of sheaves of abelian groups. I mean, for general locally compact spaces.
But is it the same for, so to say, ordinary?
For ordinary, yeah, like finite W complexes, yeah, this is just the usual. And also for all profinite sets, this is the usual drag category. But yeah, let's not go into this at the moment. So yeah, and yeah, of course you can consider sheaves spectra and consider sheaves various modules over some one ring, or you can consider also the sheaf of one rings and consider sheaves on modules. So we have this class of examples coming from sheaves, and I will actually explain what is this continuous K theory in this particular case, and the answer will be interesting and useful.
And when you write DMC, you mean not the yes triangle. But the enhanced version.
Enhanced.
The each paragraph.
Yes. Exactly. Yes. Otherwise,
the notion.
Yeah. Mm-hmm. That's right. The second class of examples is coming from almost mathematics due to faultings and originally due to faultings and was extensively studied in the book of Gaber and Romero. Almost mathematics. So the basic setup, actually a non-commutative version of it. So R will be just, let's say, the usual associative ring. I an ideal such that the square of I equals itself, and I is flat, let's say, as a right module, or alternatively as a left module. Then we can then we have this localization. So basically, extension of scalars from direct category of R to direct category of R mod I is a localization functor, and we can take its kernel, which is known as the derived category of almost modules. So this will be this gives another example of a dualizable category.
What is the localization functor?
Well, let's just say right adjoint is fully faithful.
Yes, but it's a general definition.
Yeah.
Yes, but here is it the same as saying that it's just saying that in this equation P of R I is the quotient of P of R by some category.
No, it's stronger. No, you're right. No, you're right. But yeah, okay, that's correct. But if you're asking the question how to explain this, like more precisely, like what does this mean? This means basically this is equivalent to saying that R mod I tensor with itself in the derived sense over R is again R mod I.
Yes. So you formulated the condition in the without derived words.
Yes.
Because you required flatness instead.
Yes.
But the actual condition is what you wrote here. But just when you say that, so can you write? If you are going to use the notion of localization functor, can you write the definition and maybe explain what it means when you work with the digit calculus?
Yeah, well, I would say more precisely, let's just write it here. Well, okay, it doesn't move, but never mind. Let's just write it here. So the definition, a map, okay, a functor of small stable infinity categories is a homological epimorphism. It's a kind of the correct term for such situation. If like so, if int of b is the quotient of int of a. I mean, the natural map is the natural functor from int of a to int of b is a quotient functor by some subcategory C. So equivalently, the right adjoint functor from int of b to int of a is fully faithful. And equivalent characterization is for any x and y in B. If you consider this functor like morphisms in B, so let's note this by f, morphisms in B from f of something to y, tensor maps from x to f of something tensor over A. This is equivalent to the morphism in B from x to y. Okay, and okay, let's say that okay, if we are talking just about map of even rings, then this is just the usual condition that P tensor P over A equals P.
So here the statement was that T of the functor from if you consider the kernel of the functor from T of R to T of R mod I,
Yeah.
then T of R mod I
Mod
I
T,
with the quotient
yeah.
by its kernel.
Yeah. Direct category of R mod I is the
And
quotient.
then your example, the second example, dualizable category is this C, which appears as
It's the kernels, yeah, correct. Okay, and the third class of examples, which is kind of the most interesting, comes from the theory of nuclear modules coming from the framework of condensed mathematics, which is due to Clausen and Scholze. And I will actually restrict to the case of formal schemes. Third example is I will not define it now. I'll just say that there is important category associated to a formal scheme, and consider just the affine case, affine Noetherian case. So R Noetherian ring, commutative in this case. I is an ideal, and let's just say that there is a natural category of nuclear solid modules on formal spectrum of this complete Noetherian ring. And okay, let me actually formulate the result which I have for case theory of this category, that which I hope to explain later tomorrow.
Will define what nuke means.
I will define later. Yes.
Maybe not today, but at some.
Yes, certainly. Yeah. And so basically for now, let's just say that this is important dualizable category associated to a formal scheme, and it actually categorifies the classical notion of continuous case theory of a formal scheme. So we will have an equivalence between continuous case theory in this sense of the case of nuclear modules and the inverse limit of case theory of R mod I to the n. So this is what is usually denoted by K continuous of formal spectrum of completion. And originally, when I came up with the terminology, I didn't have in mind this results. Yeah, I didn't even know about this category, so it's kind of a coincidence that the notation is compatible. Yeah.
So your motivation for the notation word convenience is
No, it's just it's a little bit random. It's rather like continuous extension, it's a little bit random. But
yes, but probably everything is providential. It's like in the
Yeah.
theory of quantum groups. So many years ago, in the 19th century, mathematicians used the letter Q for Q special.
Mhm. Mhm.
And later, this turned out to have some to be related to quantum groups. And of course, in the 19th century, quantum mechanics didn't exist. So in some sense, we can consider this as a pretty because it's and here we probably have the same.
Yeah. Okay. So this will be this I will probably try to explain tomorrow. But for today, I will first focus on. First, I will explain how in general what are these dualizable categories and how to think about them, and I will try to explain the computation of K-theory in this example and give some applications of this. I will explain how to compute the continuous K-theory for categories of sheaves.
And by the way, I think the answer is simple, so maybe you can reveal the secret.
Yes. Okay. Yeah. Let's maybe formulate it here. Yeah. So yeah, here theorem will be that continuous K-theory of the category of sheaves of modules over some one ring. Well, there is a version for non-constant sheaf of rings, but let's consider the constant one. So this will be sections with compact support with values in K-theory of R. So you consider this constant sheaf of spectra and take its sections. Yeah, everything is by default derived, of course. Sections with compact support. Yeah. Yeah. But now I will explain so what are dualizable categories? How to think about them. So first, suppose that C is computation related. Yeah, so C is incantation of picture of new topics. Then we might ask a very nice question: what are the fundamental properties of C? Like without any reference to compact objects. What do we know about the category C itself? But so let's say without using the word compact objects. The point, the main property here is that so we take some object X, C, and then X is naturally equipped with a choice with an approximation by compact object, which means that X is naturally filtered colimit. Some xi where xi are compact. And this is essentially like what we use here. So I mean, so the point of being computation rated is that you can approximate everything by compact objects. But now, so this int system is defined uniquely up to int equivalence, and so in fact, if we just forget the fact that the objects are compact, so we get a natural functor from C to int completion of C. which is usually denoted by hat, which sends x to this formal colimit of these approximations. And in fact, this functor is described by a universal property, namely it's exactly the left adjoint to the colimit functor. So we have a colimit functor which takes a formal colimit and formal fitted colimit and sends it to an actual fitted colimit. And this functor y hat is exactly the left adjoint.
Does colimit also have divided?
Exactly, yes. And yeah, we can complete this to so we have the usual ENN embedding, and colimit functor is a left adjoint to ENN. So this y hat is the y hat. We can write it also as y left adjoint to ENN. And of course, colimit is left adjoint to ENN for trivial reasons, and for this we need only the existence of fitted colimits in C. And we don't need any other condition. But this existence of y hat is a very strong condition, and in fact, it gives you one of the characteristics.
So y stands for your next.
Oh yeah, y is y is
And y hat is by definition is the double left adjoint.
Double left adjoint to another. Yes. And this actually gives one of the equivalent definitions of dualizable categories. More precisely, this is the term completely assembled. So let C be a presentable stable category. Then C is completely assembled. If this if this colimit functor has a left adjoint, so we just require this existence. Yeah.
Just and presentable and just the fact that colimit exists. It's the part of the word presentable.
Yes. Presentable
means
complete plus some assumptions.
Plus some comparing.
Yeah. Yes. But actually, let me make a remark that you can cheat and define presentable categories as follows. So C is presentable if there exists some one ring A or just a DG ring A and some A module M such that C is equivalent to the quotient of the integral of A modules by the complete subcategory generated by N. So it's just.
But you're saying that this is cheating. So does
Well,
this mean that the remark is not quite true?
No. I'm writing true statements.
This is a true statement. It's just not the best that
just not the most clarifying, I would say. And okay, if I made after I made this remark, let me also mention. So let's denote this by C subscript AM, and then another remark is that. So we have this Lurie tensor product.
Excuse me.
Yeah.
And this is in DG static.
No, it's all spectra. I mean, E1 ring just means
In E1 ring.
Yes. Equivalent to A ring. Yeah. So second remark is that so we have this Lurie tensor product, and again in this using this way of defining presentable categories, it's easy to see that tensor product of two categories associated with pairs AM and another pair of EN. This is just C A tensor B and A tensor M plus M tensor B. Yeah, so this is loaded tensor product of presentable cases. Yeah. Okay, so yeah, first definition is that C is compactly assembled. So just the existence of this twice-type adjoint to another. And another definition which
just want to add, when you write, so you take C is the quotient of mod A. By what?
I mean,
subcategory generated by M.
By colimits. I mean,
By
using
colimit.
yes, using direct sums and columns here. Okay, yeah, and another definition which is justifies the name dualizable.
But isn't the category of this one necessarily dualizable?
Once again,
In remark one, isn't such a category necessarily dualizable?
remark one. No. I mean, this describes all possible presentable categories, and not all of them are dualizable.
So you're saying any not necessarily dualizable can be still written.
Just any presentable category can be written like this. I mean, it's an exercise. Okay, so yeah, another definition that so let's again see a presentable category. Yeah, let's say everything is stable unless otherwise stated. So then C is dualizable if C is okay. It's a little bit confusing, but let's say that it's a rigid object of this category of presentable categories with the loaded tensor product. So basically, this means that there exists a dual category and the usual functors like evaluation and coevaluation with the usual properties. Yeah,
Just
yes.
So let us look at it slowly.
Yeah.
Everything is understandable if we pretend that we know what this tensor product is.
Yeah, but I just I cheated and defined it in this way.
So you gave some kind of ad hoc definition.
Yes.
This is of course a bad definition because it involves the choice of A.
Yes.
And then and such a choice, I don't know why it's called presentable, but maybe this choice of AM is a presentation.
Yeah. Yes. For example, yeah.
So if we choose such a presentation, then we know what the tensor product is. And then you already used this.
Yes.
It's a and this Lewis tensor product is something which it's not a tensor for non-concordant. Then there is naive notion.
Yes.
And this is a different.
This is different. Yeah.
It's a different. Because it involves some.
Mhm.
And then you are saying that the dualizable are just rigid functions.
Yes.
Okay.
Or equivalent dualizable objects, but this would be confusing when defining dualizable categories as dualizable objects.
Yes, I remember that at some point it's Gori told me about this Lewis definition, and it looked completely crazy and I'm not understanding.
Yeah, but I will make a comment why it's reasonable. Yeah. So okay, let me just recall maybe here that the tensor product, loaded tensor product, is just defined by universal property in a natural way that just continuous. So for me, continuous functors are colimit-preserving. So continuous functors from C tensor D to some other presentable category E is just bifunctors from C cross D to E, which are, let's say, bicontinuous. So continuous in nature. And okay,
Yes.
Yeah.
By the way, you use this notation. So you said it is dualizable, it's a rigid object of, and then you wrote
yes,
L
Yeah.
and something.
yeah, yes.
And
Stable.
I don't even see.
So what does that notation mean?
Yeah, it just means that we consider objects are presentable stable categories, and L just means that we consider functors which are left adjoints or equivalently commuting with colimits. In this case, just commuting with direct sums, because.
Okay, so it's a presentable stable category.
Yes, and the colimit-preserving functors between them. And the tensor product is a Luri tensor product. Yeah, and okay, let me just write an exercise here that C tensor D is the same as continuous functors from C to the opposites. So it's, well, it's sort of explicit definition.
This is for dualizable or
For any present.
Could you also remind me what a rigid object is? Or is that too much?
No, it's the same as dualizable object, just there exists a dual object, C2.
So again, here we have to pretend
Yeah.
that we work with usual categories, not with.
Yes.
symmetry. Most of us have to pretend that we work with the usual, symmetric moderator.
Yes.
And
But
then-
you can pass to homotopy category and just define the dualizability as a property of homotopy in the naive.
So in fact, it's a property
Yes.
is the homotopy category,
Yes.
which is a usual.
Yes.
And in a usual symmetric moderator category, there is a notion of a rigid or dualizable object.
Mhm.
And this means, so there's, you have a symmetric one. So
Yes,
this means
yes.
that you have another object,
Mhm.
and you have a evaluation map
Uh-huh.
for evaluation, and this satisfies certain
Mhm.
identities.
Yes.
This other object which is totally true is in fact unique, and in fact it identifies with internal.
Yes.
Internal.
Internal home to the unit object. Yes, yes. And let me just make a remark, again, kind of general one. So X in some symmetric monoidal category, let's say D, either the usual one or infinity category. So if we assume that the category is closed, then it's rigid if and only if just for any Y, natural map from the internal home from X to the unit tensor Y to internal home from X to Y is an isomorph. So it's another way to avoid this. Okay. Okay, so let's give just an example that in fact completely generated categories are dualizable in this sense. Example, let's for simplicity consider the category of modules over some E1 ring. This is the same as completely generated, the same as completely generated category, which is generated by a single compact object. So these are, let's give the modules over some E1 ring. Then the dual category, then it is dualizable, and the dual category is just the category of left A modules. So the evaluation functor from C tensor C dual. So this is the same as the category by modules. And this is just so if we are working over the sphere spectrum, then evaluation functor is a functor to spectra, and this is just THE with coefficients in a bimodule, and co-evaluation functor from spectra to So to this category of bimodules, it just sends the sphere spectrum to the diagonal bimodule. Yeah. So
Again, some of us interpreted spectra are the same as complexes
yes,
and
just HH over Z. Yeah.
just
Yeah.
neutral.
Yes. Yes. Yeah.
Uh, yes.
Yeah, and the same works for any computer-generated category, not necessarily by a single object. Yeah. Okay, and now let me formulate a few. First, the statement that these properties are actually equivalent, and a few other equivalent formulations of being compactly assembled and being dualized.
And is this your result or Lury's?
No, you see, it's contained in Lury's book in one assembly. Yeah, so so few equivalent definitions. Dualizable category. So the following are equivalent for representable stable category. So first is that C is dualizable. Second, that C is compactly assembled. Third is that there is short exact sequence of categories of the form to 0, C, modules over some A, and modules over B, where the map from the functor is induced by is just extension of scalars with respect to some map of E1 rings, and it is required to be a homological epimorphism. So this is just B tensor B over A to B. Yeah. So
just so if I forgot if it's a homological epimorphism, then we know that I think you told us that in this case functor of tensoring by B
is localization.
Is a localization. So
Yes.
it identifies by mod B
Mhm.
with the quotient of mod A by some.
Yeah, and there's something
claim is that something is dualizable,
Mhm.
and any dualizable categories can be appears on this.
Yes. Yeah. And okay, let me formulate also just almost the same version, but so everything is the same, but we just consider sequence where we have in completion some category which is not necessarily generated by one object, and again, so this functor from A to B is a homological epimorphism. But yeah, it's just a variation. The same property. Yeah, and okay, there are more definitions, but let me mention one of them is kind of a projectivity property for any quotient functor from D to C. I mean, inside this world of representable stable categories, there is a section C to D. I mean, section in this case, so section is supposed to commute with colimits. but it's not necessarily an adjoint functor, just some section. Yeah, and okay, let me also mention the fifth property is that C is a retract of compactly generated category. So retract, I mean, of course, in this case, representable categories.
You say the section is not required to be continuous.
No, section is continuous, but I mean,
It's strongly continuous.
it's not strongly continuous.
It's in the Q sheet will introduce motion strong.
Yes. Yes. Mhm. But I mean, it's also not required to be any kind of adjoint to this functor. It's just some section. Okay, yeah, and in fact, it's relatively easy to prove all of
When you
this.
say retract, what does it mean?
Just again, you can formulate it on the level of the homotopy category, just functors in both directions.
Yes, in a one category, I understand what.
Yes.
But here you suggest to consider even usual categories forming two categories.
Yes. Yes.
But you suggest to completely disregard.
Yes. Yes.
Consider only the one category, then when you see retract, you retract.
Yes. Yes. Okay, so it's relatively easy to prove all of this, but okay, I already explained how this y hat functor works for compactly generated categories, but let me maybe explain something which is not immediately obvious. So suppose that C is dualizable. Let's describe how to describe y hat from C to int of C. We can think of int completion as okay, just because of theoretic issues, this is contained in the category of functors from C opposite to spectra. I mean, it would be the same category if C was small, but it's not small. But let's just okay. Still, we can consider int objects as certain sufficiently nice contravariant functors to spectra, and then the explicit description is that y hat of x regarded as a functor computed on some object y. This is just a coevaluation of x box product with y dual, and sorry, it's not evaluation, it's not coevaluation, it's just evaluation. Yeah, and y dual, if we were considering modules over some ring, then this is just the usual dual, like home to the ring itself. But in general, you can define this y dual by a universal property. Yeah, I mean, basically for
the letter y is used.
Sorry, yeah. Let it be z. So home from some yeah. So this z dual is an object of C dual, and home from some other objects of C dual to Z dual is just the home from in this C tensor C dual from Z tensor W to coevaluation space spectrum. This is just a way of writing what is the dual object in this abstract setup. But again, if we're talking just about modules over rings, then this is just the usual dual module.
Okay, so I cannot say that I understand much. I would say that all this theory is with all beautiful theories. It looks locally trivial.
Yes.
But of course it isn't even. It's not trivial even locally. At the closer examination. Second, so maybe it's not the best approach to the notion of dualizable, but the good news is that you say that these are precisely reflects of
Computation, yes.
So, for instance, a projective mode would, many years ago, I learned that the projective
Yes. Yes.
Here we can pretend that 5 explains us what
Yeah, but in fact, the equivalence between 4 and 5 is more or less analogous to what you just said. Because property 4 is like
maybe yes, probably yes, because it's very is very around. I'm not sure that it's indeed the most eliminating approach, but at least we can pretend that and then maybe in some sense your theory is just again we can pretend for the moment that your theory is just by the usual procedure to have you know what is the generation category, then you can believe that you know that is maybe absolutely bad.
but not quite.
Not quite, because the notion if this probably would have been true if this case if but it's not true because K lands to not an unusual category, but infinite.
No, not for that reason. It's just because this continuous case theory is functorial only with respect to strongly continuous functors, but not.
Even
Yeah,
this.
yes.
So, but
Yeah.
okay. So this is an illusion.
Yes, that's an illusion.
This is
Yeah. And moreover, you can represent any category or any dualizable category as a retract of completely generated category whose continuous case theory is 0. So I mean, we don't have a chance to proceed like that. Yeah, but okay, okay. Let's. I will give actually a slightly more clarifying presentation of this dualizable category, but first,
and all these characterizations are so to say external in order to prove maybe except one.
well, first and second are not external.
Not external. Yes. So all the rest tells us that to prove that the C is dualizable, we have to construct something. It's not a property.
Well, I would say that force is also a property, but you need to consider all possible.
All possibilities. Yes. So it's not and yes, I'm not sure. For instance, you said at the very beginning that your first example was derived
Sheaves,
on a local phrase. And I'm not sure that any of these characterizations immediately show
yeah, but in fact, being compactly assembled is relatively easy to. Yes.
Okay. So anyway, if we know only this, we will not be able, I'm afraid it will not be able to solve simple exercises.
No, but I mean, there is a trick to show that the Sheaves condition is satisfied, and I think it's due to you, as far as I know.
So maybe
that's
so
also
it's due to a previous meeting.
Okay, so yeah, but first, suppose that we have just this bunch of prioritizations. I wanted to at first I wanted to say that the definition of continuous case theory is now somehow forced if we wanted to satisfy the localization property, which we certainly do.
But we, I think it's more or less fine for a break.
Yeah.
If it's, but the question is whether it's logical to make to take a break now.
Well, let me just make like definition in quotes, like what continuous case theory should be, like what it is forced to be. So definition, if C is the kernel of this localization, for example, of the form mod A mod B, where A to B is as above a mode of dimorphism, then continuous case theory of C has to be the fiber of the map from case theory of A to case theory of B. Yeah, it's not yet a proper definition, for example, because it's not clear why this is functorial, and also it's not clear with respect to which class of functors it is functorial, but at least the level of objects, this is how it has to be defined. But later I will make this more precise.
Typically, when you are talking about the theory, you need it includes negative.
Yeah, non-connected. Yeah,
Non-negative.
yeah, yeah.
Can we take a break?
Yes, yes.
For 5 minutes.
5 minutes. Okay, let's continue. So yeah, I just gave sort of a forced definition of continuous case theory, at least for each particular dualizable category with a chosen presentation. But now I want to explain more precisely how it works in a tutorial way. First, first I'd like to explain that in fact one can say say a little bit more about how the dualizable categories actually work, like how do they look like. And first, I want to explain that they are in fact generated by.
By the way, at some point, you mentioned problem.
Yeah.
The fact that the theory is functorial with respect to
Yes. To them. Yes. Yeah.
But I'm not sure that you gave the definition of problem.
Yeah, I will.
You will.
Yes. Yes. But first, I wanted to say more about just the properties of dualizable categories, and basically, a priori, these presentable categories, they are generated by like kappa compact object for some maybe large regular cardinal kappa. But in fact, the situation with dualizable categories is much better. We just need this countable represented object. So just something which is countably large, but not arbitrarily large. And to formulate it more precisely, so here's a lemma, which is quite easy to prove. So so suppose we have this homological dimorphism. So homological dimorphism of small categories. this functor is f. Then this category C, which is the kernel of localization, is generated by is generated by a particular class of objects, objects of the form colimit of a sequence, like I mean formal colimit of a sequence of objects of A, x1, x2, and so on, such that when we apply the functor f to each of these maps in the sequence, we get 0. And basically, the proof is quite easy. I mean, well, clearly, any such object is contained in the kernel, just because after applying f, we will get in the 0 sequence. But to prove that they generate, you just need to prove that the right orthogonal to this collection of objects is 0. And it's quite easy to construct just for any object in the kernel. You, by inductive process, you can construct an object like this with a non-zero map.
Generated means what?
Okay.
Generated means what?
By colimits. But this equivalent to the condition that the right orthogonal is 0. Yes, and corollary of this is that if C is dualizable, then C is generated by count represented objects. So formally, it's written like it's the category of omega 1. It's omega 1 featured colimits of omega 1 compact objects. Yeah, so we only need count represented objects to generate the whole category.
And omega 1 means
Aleph 1.
the first, well, it's Aleph, so it's the first
Uncountable.
uncountable cardinal, or if you prefer, the first uncountable odd.
Yes, it's equivalent. Yeah. Yeah, and the reason for this is just conventionally there is strict inequality when we talk about couple small objects. So strict inequality just means that we're dealing with countable things. So for that reason, omega 1 is the notation.
Omega 1 appears as so when you wrote omega, this means that only colimits
Of sequences.
finite sequence.
No, when I write omega 1, I consider only so. Yeah. Okay. So sorry. You mean I consider sequences in which situation?
No, let's see is what is in omega 1 of.
It's I'm adding formal filtered colimits, but now omega 1 filtered colimits. It's like okay. You can actually ignore this because this is just equivalent to the condition that C is just generated by counter represented objects. But there is a formal way to obtain the whole category from this.
So the first good news is that C is generated by how to say
Countably presented or equivalent to omega 1 compact.
omega 1 compact.
Yes, yes.
You just take the definition of compact function and instead of saying that something is finite, you say that it's not countable.
It's most countable, yes.
Yes. And so the first good news is that C is generated by such.
Mhm.
And the second good news is that C can be reconstructed
From this subcategory.
And this means that we don't have that we set that for stuff, we don't have it.
Yes, yes. So we essentially can deal just with this categories with countable direct sums, like small categories with countable direct
For
sums.
instance, you don't have to know what are accessible. So regular. So in the Lury's book for the group indexes GA4 start with some theoretical stuff.
Yes,
Should
yes,
carry.
yes.
And you are reassuring us that we don't have to.
Yeah, at least when we are dealing with dualizable.
At least
yes. Yes. I mean, still, I will consider something which is some objects which are uncountable, but at least the category can be reconstructed by count-represented objects. Yeah, and so just a proposition is that.
And by the way, for instance, in the case of the category of, you started with a simple example of a dualizable category which is not computation related. Would you consider the sheaves on a locally complex space?
Yes.
And maybe you could say something what happens in this.
Yeah, I will. Yes, but first, let me just formulate this another characterization of the level categories. Is that okay? First, definition. If T is just well, we can just say triangulated category with countable direct sums. Then we can say that a morphism between two objects is compact if for any sequence of objects d1, d2, and so on, the image of the map from well, just home from y to direct sum Zn to home from x to direct sum of Zn is contained in the direct sum of home from x to Zn. So if we take any map from y to the countable direct sum and compose with this map f from x to y, then this composition will factor through a finite direct sum of the n. And then with this definition, we can formulate another characterization that, so let's see presentable. Then following are equivalent. C is dualizable. Second is that C is generated by countable represented objects plus additional condition. So generated by C omega 1 and for any object x in C omega 1, x is equivalent, x is isomorphic to a colimit, some sequence Z1, Z2, so on, where all Zi are also omega 1 compact, and each map Zn to Zn plus 1 is compact. Yeah, so this is a little bit more like more precise explanation of what dualizability means. Yeah, so just move.
Yes. Now, so what does this notion of compactness mean?
In the compactly generated case, this is just saying that the morphism factors through a compact object.
Ah.
It's just
But good news is this definition makes sense.
In any, yeah, even for non-dualizable, yeah, can make sense of the definition.
You can also say it's generated every object is filtered colimit along contact length.
You mean any not necessarily countable? Yeah, that's also true. Yeah.
So we get a new definition of efficient dualizability, namely it should be first generated by
Well, generated by counter represented objects, and then
represented object, and each counter represented
Yeah.
can be represented as a good inductor.
Yes.
Means that's number one. It's the colimit with respect to object integers.
Mhm.
And second, more important that all morphisms are combined.
yes, all morphism. Okay, and using this, let me just explain how to see easily that the category of sheaves is dualizable on a locally compact space. For corollary, this is just one of the ways to prove this. That let's just focus on the category of sheaves of complexes of abelian groups. That this is dualizable, but the same proof works in general. So proof. Yeah, okay, I didn't say this, but in fact, this condition is sufficient to check for some collection of generators, not necessarily for all counter represented objects. And so first, so observe that this category, let's call it C. So C is generated by objects of the form ZU. So this is just the constant sheaf on an open subset which is extended by 0, but we can actually consider only those subsets which are countable at infinity. Which means that U is a countable union of just countable collection of compact subsets. I mean, it's clear that the whole category is created by this object where we consider just all possible open subsets U, but any open subset is a filtered union of subsets which satisfy this condition, and then for such U, we can find a sequence of subsets V1, V2, and so on, including sequence of open subsets such that the n is contained in the n plus 1 with a closure, and the closure is compact. So the union of all Vn is equal to U, and each Vn is itself countable at infinity. This is just an easy exercise on topology of locally compact spaces. Yeah, and then ZU is the colimit of this ZVN, and each map from ZVN to ZVN plus 1 is a compact map. yeah. Yeah, everything except for the last statement is just an exercise on on how the topology of such spaces works, and the last statement is just the observation that wait,
Alright,
yes.
Can you probably can just prove it's a rigid object. You can probably for.
You're right. The dual category is itself is the same, and we can write down evaluation and co-evaluation. That's true.
Probably.
Yes.
Easily, so.
No, the point is not to obtain necessarily the easiest proof, but just to explain this.
Yeah, but it's possible.
Yeah, certainly.
Yes.
Yes. Mhm. Yeah, so I just wanted to explain why this map is compact, but this is just because when we consider this map from sections on Vn+1, some shift to sections on Vn, shift, so this vectors through sections on Vn bar, F, and it commutes with elements.
Okay, so you have just explained that. So for first of all, as I said, maybe even before beginning of the talk, you're doing something like private functional analysis or even satiric topology. Second, here we are doing satiric topology very precise.
Yes.
And you are saying now, so if you have a local space, then in addition to the usual version of inclusion, there is a stronger notion which says that one strong inclusion.
We can say overconvergent, but it's not maybe a common terminology, but it's intuitive.
Yes. And what does it mean precisely?
Exactly what is stated here. So
that between them there is
a compact.
There is a
yes.
and then you're explaining that in this case, if you have if we're in this situation when the components one contains the other and between them, then this inclusion
is compact.
Opening, well, the map of sheaves.
The map of sheaves.
So each open determines a sheaf.
Yes.
The constant shift.
Yeah.
And it was saying that if there is a conflict between such opens, there's the morphism of shift.
Yes.
And is that converse also true?
Yes, that's actually true. Yeah.
So at least so there is a basic problem. So there is a notion of sheaf which was introduced in the 1940s. But longer than that, there was the notion of open set and because and on all morphisms of sheaves, there are such simple morphisms where the sheaves come from open subsets. In this case, morphisms precisely correspond to such morphisms. Your notion is equivalent to the very classical notion of compact
inclusion.
And this is probably one of the reasons why we call it compact.
No, I mean also just because in the computer generated cases same as factoring through a compact object.
Yes, and maybe also.
Yes, some would, yeah. Operator of finite rank, or
Operator of finite
Yeah,
rank.
yeah.
like algebra.
or compact operator.
compact operator,
Yes, yes. That's true. Yeah, and okay, since we mentioned this, let me just make a remark that we have actually a functor by head from just the category of open subsets, which is like this is a partially loaded set. We can consider it as a category, and we have this functor by head to the incompletion open of X, where U is sent to the formula limit over all Y, which are like overconvergently contained in U B, and this is this functor is left adjoint to colimit. Where colimit in this case is of course just the union.
So. Okay, just. So, so here we forget about the category sheaf and just consider that the category of open subsets for that. In particular, since it's that's very responsible for limits.
Yes, and they do.
And of course they do, and they are quantity.
Yes.
Or maybe, well, in the general process,
Jones, yeah. Oh,
the same as.
so it's the same as supreme, yeah.
And then, now, but for limits, as you said, the functor of taking the limit is the next.
Left adjoint to N.
But now you have Y hat is the right edge.
No, my head is the left adjoint to the
It is a double.
double
adjoint
adjoint, yeah.
ladder, or which is the same as.
Left adjoint to colimit.
So, and you are saying that in this case, this Y hat is.
Yes, and it's given exactly by.
Maybe it exists, of course, in bigger category of sheets, but it's convenient. But you are saying that if you apply this one to opens, then you only care about the
Yes.
and just be represented as a nice.
Yeah.
So there are many presentations of an open subset as a union.
As a filtered union.
As a filtered union of open subset, for instance, this way
Just the
open
subset.
subset. It's and this is union.
This is union.
But then there is an more intelligent way of representing this open as the intelligent. You consider all opens which are compactly contained
In U. Yes.
then you observe that such opens form a filtered set.
Yes.
The union of such opens is if you have two opens which are compactly contained, then
I can take the
union. And so we have this, and then we have this presentation, and this is quite heavy.
Yes, this is quite heavy. Yes.
Actually, when I went to the website, which is Lab, I found that long before Luri, there was by
Joel and Johnston.
yes, by Joel and Johnston, who introduced this notion
Continuous category, yeah.
a notion which we get called continuous category. In the context of usual categories, and even before that,
There was a notion of continuous partial.
there was a work for the notion of continuous.
Yes.
And maybe before that there was something about linear. So anyway,
No, I think before that there was nothing.
I think there was there was something. There was some work which was done by a person who did something algorithm there, something which looks like. So the story is very strange.
Yeah.
Maybe even
Yeah. And actually, this continuous partial set also give examples of dualizable categories. Yeah. I will mention at least one example.
So maybe well, many years ago, dedicated invented dedicated. I wonder whether dedicated secret will something about do real numbers for the continuous.
If you attach plus infinity, then yes.
You attach.
I mean, you need to do limits.
So that we need have to attach the plus infinity for the continuous.
Yeah. I will actually mention this. Yeah.
Yeah, but is it limit or colimit?
Oh, so sorry. I can. Yeah. Colimit. Yeah. Okay. So this was an example of how you can show dualizability. Sorry, again, retraction. Well, I don't have to, but this can be done.
Yeah, but probably just based on this way. Just a little bit.
That's true. But okay, let me make another general remark about retracts. So let's see dualizable and D some quotient functor, like for example, for quotient functor inside presentable world, like for example the sheafification functor, sheaves to sheaves. Then there is a very particular section of the form, just canonical choice. Form C goes to so yeah, this function be f. C goes to int of t by another head. Then we just take int of the right adjoint, going to int of d, and then take colimit functor to d. So we get this functor from C to D, and this is the section of f. It's just a very general way to think this section canonically. Okay. So now let me finally define continuous case theory like more rigorously, and also explain the functoriality. So first, the definition so let's just restrict to dualizable categories. So let C and D be dualizable. Then F from C to D strongly continuous. If well, first it has to be continuous, so which means just existence of right adjoint functor. But so we not only require its existence, but we also require that it is continuous. So this is the strong continuity, and so this PR dual will be, well, PR stable dual will be in the category of dualizable categories and strongly continuous functors. Yeah, and an easy observation proposition that if we consider, yeah, okay, let's just say that this cut infinity curve will be the notation for this category of small categories, small stable infinity categories, which are Karubi complete. And so we have a functor to PR dualizable, which is int completion. Because as I mentioned, all completely generated categories are dualizable. And then, so this functor is fully fixed. So this is basically saying that if we have completely generated categories, then a continuous functor is strongly continuous if and only if it takes compact objects to compact objects. So this is just a reformulation. Yeah, so in this way, we can consider this category of dualizable category as some bigger category than the usual category of small. And now, yeah, let me also make a remark. Yeah, let's make it here. So remark, functor strongly continuous if and only if we have a commutative square. So like okay. Let's assume that it's already continuous. Then we can consider this y hat functors from C to incompletion and from D to incompletion, and we will have a natural transformation from one composition to another, and it is required to be equivalent. Just equivalent way to formulating that the functor strongly continuous.
Just a moment, I will try to write it down.
Yeah.
And at some point, maybe you can tell us. Oh, the baby, it's interesting. Interesting graph of the information. Category is the category of sheaves that play complex space.
Yeah.
And we know that there are some standard functors between such categories.
Yeah. Pull back, push.
Well, probably there are 4 such functors.
Yeah.
And some of them are continuous functors of knowledge, and some of them are only continuous.
Yes.
Maybe help.
Yeah, that's.
But I didn't have time to write down what this is. We have a functor F from C to D.
Yes.
And then it's saying that it's stranded.
Yeah, I already implicitly assume that it is continuous, and then yeah.
The continuous F. Continuous. And then can you say it again?
So we have this we can have this functors y hat for the category C and for the category D. And now we can consider composition first go from C to D and then apply y hat, or the other way in the other order. First apply y hat and then just take the incompletion of our functor. And there is a natural transformation from the first composition to the second one.
And we want it to be
equivalent. Yeah, equivalent. Yeah. Okay. So now let's actually define continuous case theory.
Yeah, but just a moment. Can you tell us which standard functors between sheaves?
Yeah, let's I'll explain. Remark that let x and y offer a compact Hausdorff. Then f is a map from x to y. Then like f upper star. Yes, suppose that we would take sheaves, for example, with values in 0, z. Sheaves on y, sheaves on x, 0, z. And this is strongly continuous if and only if f is proper. Just because the right adjoint is a push forward and requiring that it commutes with colimits is the same as properties.
Maybe before strong continuity, let's discuss usual continuity.
Okay, it's always continuous just because it has a right adjoint. Yeah.
So we have there are 4 functors.
Yeah.
4 standard functors, but they split into 2
Adjoint pairs. Yes. Yeah.
And in each such pair, the left functor is
Automatically continuous.
automatically continuous.
Yes.
So we have the star pullback and the shriek
Push forward, which are automatically
continuous.
Yes.
And moreover, we know their right adjoint.
Yes.
They also have.
Yes.
And now you are saying that in this case, the right adjoint to F star, F upper star, is F lower star. And if F is proper, then F lower star is the same as Schmidt.
Yeah. So it is continuous. Yeah. But also the other implication also works. And about strong continuity of F lower shrink, it's a more complicated condition. Maybe we can mention it later, but it's more tricky. For example, if you consider the projection to a point, then requiring that shrink push forward is strongly continuous. It's a condition on the local behavior of the space. It's close to what in the modern languages like local contractibility, but kind of generalized version of local contractibility.
But for smooth morphisms,
yeah, that's perfectly fine. Yeah.
Because in this case, so if you have the shrink push forward, it's always it's the right adjoint.
F upper shrink.
Upper shrink.
Yes.
But it will largely.
If it happens to be continuous,
and the morphism move in some sense.
Yes.
Then it is equal to upper star.
Up to 3, yeah.
And therefore, we see that.
Yes, exactly. Okay, so this was a remark about continuous functors between sheaves. Now let me make a definition. So, first, if C is completely generated, first, if C is small, stable, then calculation of C is just the quotient of C by compact objects and take care of the completion. And also let's mention the countable version of this. So calc n omega 1 of C is just the quotient of count represented objects by compact objects and again current completion. Now, like if C is compactly generated, then we define this continuous Calkin category of C just to be the Calkin category of compact objects. Very nice observation, kind of useful here, is that this category makes sense even if C is not completely generated, but only dualizable.
Sorry, so in part one is when you say C mod C omega, but you also wrote C as a small scale.
Which is, sorry, yeah, sorry, int of C modulo C. And here it's countable int completion modulo C. Sorry, thank you. So that would be the definition for the second case. Yeah, if we write it down. Yeah. So yeah, if C is completely generated, then continuous Calkin category of C is just the Calkin category of the compact objects, and similar to the countable version. Yeah, okay, similar for omega 1 version. And third is that if C is dualizable, we just define, let's just consider this countable version, and we define it using short exact sequence. We have C, we have the functor y hat, but in fact, from this generation by count represented object, it follows that the image of y hat is contained in the int completion of C omega 1 count represented objects. And the quotient by the image is automatically compactly generated. And I just define the Calkin category to be the compact objects in the quotient. Countable Calkin category. So it's somehow it can be sort of as a virtual quotient by compact objects. So even though we might have no compact objects at all, like no non-zero compact objects, we still have a notion what is a kind of virtual quotient by that.
So here where something important happens. So suppose we have, so in the compactly generated case, now the C is only dualizable, and 3 is a 2 and 3 agree.
Yes, and this follows just from the fact that if you have a short exact sequence of small categories, then after you take int completion, you again get a short exact sequence. It's just, I mean, it's due to Niemann, I guess, in this formulation.
Moment. How do we know that? So what we'll do if C is dualizable? You have this y hat.
Yeah.
And then you take the quotient.
Yeah. So first, I'm observing that the image of y hat is contained in this subcategory, just in completion of the countable guys, and then I'm taking the quotient, and the quotient is automatically compactly generated. So it's just this can be considered as a definition of this.
And why is it?
Just because the image, because the right adjoint to y hat commutes with colimits. So we have this right adjoint functor, which is colimit functor, and it commutes with colimits. So this right adjoint functor also commutes with colimits, and using this, you immediately deduce that the image of a compact object is a compact object, and these images generate this quotient category.
To get an object called count, yeah. you take
It's quant.
quant.
Yeah.
You first consider the quotient of int omega 1 by C, and then you observe that this quotient is computationally related, and you take the normal function.
Yeah.
And if instead of omega 1 you put here omega 2,
Yeah, any regular cardinal. Yeah.
But omega 1 is the simplest.
Yeah, it's the simplest. I mean, it's the smallest, which is sufficient.
But anyway, the good news is that you don't need.
Yeah.
You don't naively you would like to take in.
Yeah.
But this this is unsafe.
Yes.
And you are saying that it's enough to take C omega 1, but you need to take C.
Yes. Yeah, and then we can make this definition, kind of functorial definition, yeah, I'm defining continuous case theory, but the same works for any localizing invariant. So continuous case theory goes from dualizable stable case theory to spectra, and so continuous case theory of C is defined to be shift by -1, so it's omega of k of the countable continuous Calkin category. And yeah, and in this case, we don't have to make any choices, just literal definition. Just because the Calkin category is functorial, yeah, so we get a well-defined function.
Very good. And my understanding is that Calvin himself didn't care about each category.
Yes.
He was a functional analyst.
Yes.
And he defined what is called the classical Calvin algebra.
Yeah.
And this is what you have a Hilbert space, for instance, so
Yeah.
one space, and you take all operators.
Yeah, so he was considering bounded operators on this Hilbert space and modular, yeah, compact thing. Yeah.
And this is the classical notion of Calvin.
Yes, but now
There is also a use for algebraic analog one instead of the Hilbert space.
yeah, but
countably generated model operator, and instead of compact operators, you take operators in final range.
yes, but it's just a kind of an exercise. Let's just consider the case of a field. So if K is a field, and V is a vector space, which might be just the usual vector space in degree 0, then just endomorphism of V in the Calvin category of K. In this sense, is just endomorphisms of V modulo with status of V. So it's, yeah, we get this algebraic version of Calvin algebra.
So for compactly generated categories, it was known, maybe it was known that when you pass to the Calvin category, then the case theory is
Descripted by
one in some
Yes.
and so your idea is that after Calvin, the difference between
Dualizable and compactly generated. Yes. Yeah, so basically Calvin construction makes everything compactly generated. I mean, if you define Calvin construction in terms of large categories, then in dualizable categories, it becomes compactly generated. Yes. Okay, so then, let me state some properties which are actually not difficult to check. The position is that this continuous case theory commutes with restricted colimits. There's one observation. But restricted colimits taken in this case for dualizable categories. Well, actually, you need to understand how the restricted colimits work. So it's not like immediately obvious, but it is not difficult to show using this general criticalizations of dualizable categories. Second nice property is that we have this commutation of case theory with pullbacks under certain conditions. So consider like functors from A to C and from B to C. Everything happens in this world of dualizable categories, and requires that the functor from A to C, let's say, is a quotient functor. Then the fiber product, the naive fiber product, is also dualizable. And continuous case theory, the fiber product is the fiber product of continuous case theory of A, B, and C. Yeah, so it is not difficult to check, but let me just not do it now. And using this general properties, so I promised the computation of case theory of sheaves, but let's do it for the real line, which is quite instructive. Yeah, let me just mention that the second corollary covers results on excision, but gives on excision in case theory, but gives simpler and shorter proofs. Let me just not go into that now, but just simplifies the classical statement about excision in case theory. Okay, let me just explain in some detail how to compute case theory for sheaves on the real line, because this somehow clarifies how this case theory works. So just a remark about sheaves on the real line is that if you consider sheaves on R with values in modules over some ring. So yeah, this is MATBD and this is.
Can you use another?
Yeah, okay, you're right. Let's let it be. Okay. So so the category of compact objects is just 0, and I mean you can more generally characterize what are compact objects in this category of sheaves. They must have compact support and be locally constant with perfect stacks. But in this case, this is just there are no such compact objects, so this is just a 0 category. But still, case theory makes sense, and so theorem in this case says that continuous case theory of this category of sheaves is a sheaf by -1, so it's omega of K-theory of A, this Ivan ring. So let's just compute it, so to say, by hand.
So for instance, K0.
Yeah, K0
is K1 of A.
Yes, so K0 of this sheaves is P1 of A. And more generally for Rn, we'll have K0 equals Kn. Yeah, so how this explicit computation works. So recall that there's a notion of single support for sheaves on at least C1 manifolds, which is explained in the book of Kasprowski and Winges. And I mean, they study it in great detail. They also prove that it's always coisotropic, which is actually much more difficult than Gaber's theorem, so to say, in this sheaf context. So there's a very general, general notion, and they prove a lot of results about it. But I will just consider a very special case where single support is very easy to understand. So, so kind of proposition, proposition definition. That for.
And the reason is that on the real line there are only two directions.
Yes, yes. Roughly.
Essentially, two elements is very.
Yeah, yeah. Yeah, and I will essentially consider shifts with single support in one of the half planes. So for F, in this category of shifts, the following are equivalent. So first, that it's single support. Okay, let's say it's proposition definition. So it will be definition for people who don't know what single support is. So it's that it's contained in the non-negative part of the Cartesian bundle. Second condition is that for any A smaller than B, the map from sections of F on the ray from -infinity to B is isomorphic to sections from the interval A to B. Yeah, and yeah, so basically, this category of sheaves with no negative single support. This is just the category of functors, let's say F from the partially ordered set of real numbers, with the opposite order, to any modules, as that for any real number A, F of A is equivalent to the limit over B smaller than A of F of B. Yeah. And now it is well known. Well, I get yeah. There is a reference for the statement due to Tamarkin. I think that the inclusion has a left adjoint. Yeah. So this is yeah. Yeah, and also by the papers of symplectic geometers like by Ganatra, pardon, and Schende. Yeah. So this is kind of well-known statement, and it can be even described explicitly. But in this situation, we can say more. We can observe that there is a pullback square of categories. So we can observe that we have a pullback. So we have this sheaves on R. We go by the left adjoint to sheaves with non-negative single support. And also similar function for sheaves with non-positive single support. and sheaves supported on the zero section, which are just constant local systems. So this is just the case of A modules. And all the functors are left adjoints to the inclusion. Yeah, so okay, if I identify this with the case of A modules, then these functors are just sections with complete support. Well, okay, after a shift. And these functors can be given explicitly by a kernel object free object of the product. So yeah, so we have this. So this is pullback square. And all the categories are dualizable, and all the functors are strongly continuous, and all of them are localizations just because they're left adjoints to the inclusions. Yeah.
And the lower right.
Yes. Yes.
There's a local system.
Yeah.
And so this is very nice.
Yeah. Yes. And so K continuous applied to this square is also pullback square. So we are reduced to showing that continuous case theory of this category of sheaves with non-negative single support is 0. Yeah. And this is yeah. So I mean, it's clear that this is sufficient because then this pullback square exactly means that case theory of the category of sheaves will be omega of the case theory of A. And this is a pleasant exercise, like in almost mathematics. So let me explain it just exactly how this works. So we have a short exact sequence of categories. Yeah, short exact sequence 0 to sheaves with non-negative single support. Then using that the description, it's hidden behind that word, but it's a description in terms of functors from the partial ordered set of real numbers. So we go to functors from the post set of real numbers, but with the opposite order to A modules. And then we go to A modules. Sorry. We go to the product of real numbers of copies of the category of A modules. Yeah, where this functor, let's call it phi of f, computed, I mean, its component corresponding to the real number A is the cone of the map from colimit over B greater than A, f of B, to f of A. So, okay, more precisely, this functor phi is a quotient functor.
Yeah. What's going on? So you said before it's written on the sheet blackboard.
Yeah.
That sheet with singular support, non-negative support.
Yeah.
Those functor which commute with some kind of
limits. Yeah.
limits.
Yeah.
So we commute with some.
Yeah.
And now probably you are just suggesting to rewrite what it means to commute with.
Almost, but I'm now here. I replace limits with colimits. But this is like this the same as the usual equivalence between the rest complete objects and the torsion objects. So it's like passing to double right or double left orthogonal. Yes. So I mean, so you have this quotient functor, and the image of the right adjoint is an admissible subcategory. So the inclusion has both the left adjoint and the right adjoint. So you can take the right orthogonal, left orthogonal, and their equivalent, and the left orthogonal is just this, is just the kernel, and the right orthogonal is the category which was it, which I described previously. So, but up to the standard, standard observations, yeah. So we obtained this short sequence.
The left orthogonal and right orthogonal are not the same.
They're not the same, but they're automatically equivalent as always for an admissible subcategory. Okay. So yeah, and the fact that this functor is a localization is just so phi is a localization. So it's indeed a quotient functor because the post set of real numbers is a dense linearly ordered subset, linearly ordered set. Just because between any two real numbers, there is another real numbers strictly between them. Of course, quite a lot of them. But this is the only kind of algebraic property of this ordered set, which is required for this function to be a localization. So this is again the almost mathematical situation. So roughly speaking, we consider the identification of this partial ordered set. So just consider the category with the same object, but now the morphisms are just either A or 0. I'm describing the combo generators. So basically, it's like having a ring with many idempotent elements corresponding to all real numbers. And we mod out this non-unital ring by an ideal which squares to itself and which is flat. And so we are again in this almost mathematical situation, but kind of a version with many objects. Now, okay, so we want continuous K0 of this to be 0, but this is the same as saying that continuous K0 of this maps isomorphically to this, but these categories are completely generated. So basically, what we want to prove is that usual case theory with compact objects, in this case, we have functors, to the direct sum over R of K theory of A, which is exactly like K theory of compact objects here. We want this to be an isomorphism. But this is just the observation. But the category of compact objects, in this case, are functors from real numbers to not A. Has the same orthogonal decomposition, but infinite one. Has an infinite same orthogonal decomposition into copies of perfect A modules. So basically, for both of these categories, after we pass to compact objects, they both have same orthogonal decomposition indexed by real numbers with the same components, and the functor is compatible with the same orthogonal decomposition. So this means that because
what is this semi-orthogonal decomposition?
Sorry?
What is it? This semi-orthogonal?
No, I mean you just take representable functors by particular. You take any particular real number E, and you take representable functor. I mean a linear envelope of a representable functor. Yeah. These are compact generators, and they are orthogonal in one direction. Yeah. And basically, what happens is we have a functor which is compatible with semi-orthogonal positions and induces identity. And I mean, the only psychological difficulty is that the semi-orthogonal positions are infinite, but K-theory commutes with restricted colimits, so so we can reduce to finite positions.
It gave us a course on DVSR, so it's, if it was a finite set,
Uh-huh.
it would be the DVSR theorem.
Yeah, but it's also called additivity. Yeah. Mhm. Yes. Yeah, so I'm using basically. Yeah. But so I'm using. Yeah, it's also. I think it's called by Hausdorff called this additivity. Yeah.
Okay.
Yeah.
So
Mhm.
know what they don't.
Mhm.
It's called.
Okay, so basically I'm using this additivity in finite semi-orthogonal positions, but and also just use the commutation with restricted colimits. So just this implies that that K-theory of compact objects here is the same as K-theory of compact objects here. So we get equivalence. So continuous K-theory of sheaves with non-negative singular support is indeed zero. And this finishes the application in this case.
And we never use the definition of the theory, we just use it's a functor with a certain property.
Yes, we only use the localization property and the commutation of restricted colimits. And so the theorem could be formulated for any such class comparative. Yes, that's true. And also the general theorem for sheaves on locally compact spaces also requires only this properties. Yeah. And so, yeah, my plans were maybe too ambitious for one talk, but I can.
Yes, I think it's already time finished.
Hmm? Hmm?
I'm sorry. So tomorrow we meet a slightly different time and a slightly different student.
But the difference is 3:30.
Yes, we meet at 3:30 and the room is towards.
Okay.
Now, so if you want to add one, please add them, but not more than one.
Yeah, let me just mention what I wanted to explain using this. Yeah. So, okay, maybe I will not give you the detailed proof of that theorem for any locally compact space, but I'll just, okay, I already mentioned the formulation. I will recall it maybe tomorrow, but maybe I will not go into details of the general theorem. But I want to explain. So, okay, so tomorrow, what I would like to start with tomorrow, because eventually I want to prove that K-theory commutes with certain nice inverse limits, which is like relevant for these nuclear modules. So I want at least to explain why K-theory commutes with products. And I just wanted to explain that this machinery with considering sheaves on the real line gives you essentially a formal way to prove such statements about K-theory, just reducing everything to K0. And so K0 is kind of an exercise for Olympiads. Yeah, so.
Just a moment. So product. What about usual product? Yes.
Yeah,
then is it obvious that
it's not obvious.
Why is it not obvious? I don't remember the definition of K-theory.
Yeah.
But I imagine some simplicial set and so on.
That's true, but the products of simplicial sets are not exact in the Quillen model structure. So if you naively consider like the simplicial sets, okay, yes, then they agree with products, but they're not. They're not the same as commodity.
Is the problem with finite products or with infinite?
No, infinite. I mean, for finite there is no.
For finite there is no problem.
Yeah,
And
yes.
by the way, why is there no problem for finite?
No, it's just the same as direct sum. I mean, it's additivity. Yes.
But for infinite products, you are saying that it's not obvious.
Yes.
But was it known before?
This wasn't proved for stable infinity cases. This was proved recently, like 5 years ago or something. But the proof is really horrible, And I just wanted to explain a very natural way to prove this, just using the machinery of sheaves on the real line and dualizable.
But it's impossible to explain this today if you wish to explain it.
So tomorrow, yeah. Yeah. Mhm.
So you are saying that already for for non for traditional criteria of
Yeah.
notation with infinite products.
It's not obvious at all, yeah. Yeah. I mean, already for K0, it requires.
But for K0, for K0, it's.
No, it already requires a little bit of thought. You need a criterion when the objects have the same class. I mean, if you just naively consider these relations coming from triangles, then you have no guarantee that you need only find uniformly bounded number of these relations. So already for K0, you need to do something. But what I'm going to explain is I will explain this actually not a difficult trick to prove this for K0, and then explain how to deduce the statement for all K groups just using this sheaves and Kalkin constructions in using this operation.
But you will explain it tomorrow.
Yes. I mean, today I think people are already tired.
Are there any questions? Let us thank the speaker.